In this video, we discuss how temperature affects the equilibrium constant. And we're going to do this in light of Le Chatelier's principle. Before we discuss how the temperature affects an equilibrium constant, we have to introduce a new concept, which is the concept of the reaction energy. Think of a generic equilibrium, A to give B. Okay? And then what we're going to do is see what is the energy requirement for this equilibrium, for both of the reactions of the equilibrium. And we're going to do this by drawing something that is called an energy diagram, which simply tells you how the energy changes as you go from reagents to products. Okay, so in the y-axis, I'm going to draw the energy, and in the x-axis, I'm going to draw something that is called the reaction coordinate, which is just a measure for the progress of the reaction from reagents to products. To the left, we're going to have the reagents. This is what we call the reaction coordinate. And then to the right, we're going to have the products. I'm choosing, in this particular case, to draw the energy of products as higher than the energy of reagents, but this does not need to be the case all the time. Okay? All right, so we complete the reaction energy profile by drawing a curve that is like this, and this is what we call the reaction barrier, which is the minimum energy that you need to react. Okay, so in this particular case, what we have is that we can try to track what are the energy requirements or the energy involved as you go from reagents to products, right? So the change in energy in going from A to B, which is a forward reaction, notice that you need to supply energy, that is a positive energy, and this is what we call endothermic. Okay, this will be an endothermic process. And what this means is that this requires the supply of energy. Unless there's some energy around, the reaction A to provide B won't happen. Okay, now we can also analyze the energy change in the reverse reaction, right? So you go from B to A, and in this case, notice that because B has more energy than A, when B reacts to A, there's going to be some excess energy that is actually going to be released into the reaction medium. Okay, so this is what we call a negative energy. This energy will be lost generally as heat to the medium, and this is what is called an exothermic process. Okay, so now we're ready to try to understand what happens to this equilibrium once we change the equilibrium, the temperature. Okay, so let's suppose that we modify this equilibrium by elevating the temperature. Okay, so we make the temperature go up. Well, let's see what the prediction of the Chatelier principle would be. Right, the disturbance in this case is an excess energy. When we elevate the temperature, we're putting more energy into the reaction medium. Right, so then the system will shift to try to minimize that excess energy that you have. Now, there's only two ways to react to this. You either go from reagents to products, or you either go from products to reagents, right? Because what we're trying to do here is minimize the excess energy that we have. We would like to absorb that excess energy as opposed to just produce more energy, right? So there's only one of the two directions you absorb energy. And in this particular case will be the endothermic process, A to give B, right? Again, notice that when you elevate the temperature, again, you put more energy into the reaction medium. A way to minimize that excess energy would be to absorb it. And that means that you're going to be promoting the reaction from left to right. That's what will happen, right? So the system is going to shift from left to right. And what that means is that you're going to generate more products at equilibrium, at the new equilibrium, than you had before, right? So what will happen is that your K prime, which is the equilibrium constant at the higher temperature, okay, notice that this is going to be your concentration of B at your temperature T prime over the concentration of A at the temperature T prime, right? Notice that because we're displacing the system from the left to the right, what will happen is that you will have more B at equilibrium than you did before, and you will have less A at equilibrium than you did at the lower temperature. So what that means is that this K prime that you're having is going to be larger than K. Okay, so if you elevate the temperature in this particular case, then the equilibrium constant goes up. That is what happens. Right, we're going to repeat this, but now for a slightly different reaction. It's going to be C to give D. And in this particular case, the energy diagram is going to be slightly different. It's still going to be the energy, and that is still going to be the reaction coordinate, but I'm going to choose C to have higher energy than D. Okay, we can complete the reaction energy diagram. That will be the barrier. Okay, and now notice that the change in energy as you go from C to D will be negative. Okay, that's energy that is being given off because D has a lower energy than C, and this is what we call the exothermic direction. And then the change in energy in the reverse process, D to give C, notice that you need to supply some energy to produce that. That is what we call a positive energy, and that is going to be endothermic. We're going to do now the same experiment. We're going to elevate the temperature and see what happens to the equilibrium, how does the reaction shift, and then see what happens to the equilibrium constant. All right, great. So if we elevate the temperature, then again we're putting excess energy into the reaction medium. And according to the Chatelier's principle, the system is going to shift to alleviate that disturbance. So a way to alleviate excess energy is to absorb it and remove it from the reaction medium. And that means that you're always going to absorb it, right, in the endothermic direction, which in this case is D to C. So then what will happen is that the equilibrium, the resistance will shift to the left, okay, because the left, D to C, is the endothermic reaction, the reaction that absorbs energy and tries to minimize the disturbance of elevating the temperature. Now notice though that the equilibrium constant is going to be a little different, right? So notice that if we have D to C, what will happen is that you're going to have an ever increasing amount of C in the reaction medium, and then an ever decreasing amount of D in the reaction medium, because the equilibrium constant, this K prime, is the concentration of products at equilibrium at this temperature T prime, and then the concentration of reagents at equilibrium. The key here is to recognize that again we're reducing the amount of D and we're increasing the amount of C. So in this particular case, your K prime or your K decreases with temperature. Okay, so again, because we are promoting the amount of C, promoting the amount of D. All right, so in summary, what happens here is that when you elevate the temperature in reaction equilibrium, the system is going to move in the endothermic direction. Sometimes that direction is reagents to products, some other times that endothermic direction is products to reagents. That is going to mean that the equilibrium constant will either increase or decrease depending on what is the endothermic direction. Right? So if the endothermic direction is reagents to products, then the equilibrium constant is going to increase with temperature. But if the endothermic direction is products to reagents, then what will happen is that the equilibrium constant will decrease when you increase the temperature. Okay, so this video has introduced how temperature affects equilibrium in the context of Le Chatelier's principle.